Hi, this is Sarah Camp doing my first physics report on constant velocity motion. I observed a rolling mouse cat toy and applied the momentum principle with an assumption of zero net force. This assumption proved to be a good assumption because of my computer model. My model was a good prediction of observed motion in one direction over a short amount of time. Here's my clip. I made the origin the center of the toy, and the toy is moving in the positive x direction along the x-axis. I used the center of the toy as the average position and tracked motion over a time interval of 0.8 seconds. I used the calibration stick to set the length scale of the video and measured the toy at 5 centimeters or 0.05 meters. Notice the toy is in constant motion over the entire. To predict motion, I used the computer model to the right. I needed the mass of the toy, which I found to be 0.023 kilograms, the initial position, which I set at 0. You can see all of this outlined to the right. And the average velocity, which I found to be 0.44 meters per second. I found that using the displacement in the x direction of 0.35 meters divided by the total time elapsed, 0.8 seconds. I assume that the mouse is moving at this average velocity for the duration of the clip. On my computer model, I made net force 0. As you can see on my calculations on the left, the final velocity and the initial velocity are the same because they are both the average velocity, making the net force have to be 0 for that statement to be true, and for the system to move at constant velocity. This is what happens when you run my computer model. The ball here represents the mouse toy, and when you run the model, you see that it moves in the positive x direction at a constant velocity, as you can see by the position versus time graph that comes up. The best way to analyze this data is to plot both the observed data and the simulated data on the same plot. The orange squares in the back of this line are the simulated data, and the orange diamonds at the front are the observations. As you can see, the simulation is a good fit for our observations in that they both go in the same direction at the same velocity for a constant velocity. So what if we had chosen a different origin? Well, the mouse toy would still become more positive, as shown by the previous simulation. It would just start at a different location, as shown here. So if we change the ball position, which is the same as changing the position from the origin, and we run the module, we see the same trend happening with constant velocity, just starting at a different location. If the origin was closer to the start of the wind-up mouse, we would have seen the initial acceleration, which would have been recorded as an apparent initial net force. However, how I chose to do it, this wasn't. So what does all of this mean? Well, because the model was a good fit for our observations, we know that velocity was constant and the net force was thus 0. This means that the total pushes and pulls on the system sum up to 0. Some of these pushes and pulls include the toy's wind-up motor against the friction or air resistance, gravity to normal force, and there's a ton of other pushes and pulls and forces that are acting on the system that are too numerous to count. Basically, what we've said here is that for net force to be 0, there will be a constant velocity, and if net force is not 0, the velocity will not be constant. A positive net force will cause an acceleration in the system.